Hey guys, welcome back to my YouTube channel. It's 2022. You want to hit that subscribe button and turn on your post notifications so you know every time I post. Well, hello there. Welcome back to my YouTube channel. So this is question 3 of our little mini series for the 2021 Physics Paper 2. And as I said, I'm doing this in parts because I'll be going through content as well. Well, question 3 will be a bit shorter, seeing that, hey, it doesn't have as many questions and the questions are mainly definitions and such. So let's get right into it, right? So 3A says waves can be described as either transverse or longitudinal. And part 1 wants you to explain what is meant by a transverse wave. So for those who don't know, a transverse wave, right, let's back this up a bit. So a transverse wave is one in which the direction of oscillation is perpendicular no. Perpendicular to the direction of motion. All right? And that's exactly what a transverse wave is. So, boom. Let's pull this down a bit. No, bro. Okay. So basically, if this is your equilibrium line, your transverse wave will oscillate up and down, up and down. However, the wave will progress from, let's say, if we choose a particular point on your wave like this, eventually, while the wave continues to move and such, it will follow this path and eventually end about this point. And that means that this first dot number 1 here moves to point number 2, which means it moves from left to right, while you can see here that the oscillations are going up to down. And if you connect these lines, you'll see that they are perpendicular or at right angles to each other, where you'd get a 90-degree angle. So yeah, I hope that's clear. So part 2 wants you to give an example of a transverse wave. Now, any electromagnetic wave would be a transverse wave, and also tides from the sea, those are transverse waves as well, because you'll see that the sea looks like this, the tides. So examples of electromagnetic waves, or the types of electromagnetic waves, are radio waves, microwaves, and sure you put waves at the end, I'm being lazy. Microwaves, then what comes after that? I believe infrared, then visible light, then what's after visible light? Ultraviolet, then X-rays, then gamma rays. So radio waves have the lowest frequency, then microwaves, infrared, seeing that on the rainbow it's red, orange, yellow, green, blue, indigo, violet, in that order. The red color on the rainbow has the lowest frequency, while violet or purple has the highest frequency. Hence, the wave below or of lower frequency than visible light would be just below red, which is infrared, where infra means below, right? And ultra means above or beyond. So the higher frequency would be greater than the highest on the electromagnetic spectrum, which would be violet. So ultraviolet, right? So yeah, another thing that you should know is that wavelength is inversely proportional to frequency. So wavelength, given the symbol lambda, is directly proportional to 1 over the frequency, 1 over f. So that means that if the wavelength increases here, for example, then the frequency decreases, meaning you can think about it that if you have point A, point B, it will take a longer time to get to point B, so you'll get there less frequently than if you were supposed to consider a wave looking like this, for example. Now remember, point A would be on the first crest, point B on the second crest. You definitely get to point B on the purple line way faster than point B, and you'd realize that on the purple wave that I just drew, you'll definitely be getting to crests more frequently than on the first blue wave that I drew. So yeah, now part B wants you to define the term ultrasound. Now anything that is ultrasonic has a frequency above 20 kHz, kilohertz, right? Which is 20,000 hertz. So an ultrasound is a sound wave as said here, sound wave with a frequency above 20 kilohertz, i.e. that is 20,000 hertz, right? So that's an ultrasound. Now they want you to state the application of ultrasound. Ultrasounds are usually, you can use them to see or get an image of different parts of the body. So you can do a pelvic ultrasound, a uterine ultrasound, which is usually a fetal. That's not how you spell fetus. Is it F-A-E? It's F-E. I know you can spell it a different way now, but I'll spell it the simple way. Fetal ultrasound. You can also use it to locate cracks in different material. For example, metal pipes, right? And that's just because the ultrasound, you sending a very high frequency sound wave at a certain speed can help you to calculate the distance that the sound wave traveled, right? Because the speed of a wave is equal to the wavelength multiplied by the frequency, or the speed is equal to the wavelength divided by the period, right? Because remember, the period and time shares an inverse relationship. So time is equal to 1 over the frequency, or not time but period is equal to 1 over the frequency, and also frequency is equal to 1 over the period. So yeah, simple enough. As I said, this one's going to be short because the paper almost finished. We have about 3 questions left. So part C, figure 3, shows the path of a light ray through air through a cube of ice, along with 2 rays showing, what's that? Partial reflection. So let's examine this for a bit. So on the plane MN, this would be your incident ray I, and this would be a reflected ray R. Let me use common R. Now the angle of incidence is measured from the normal. So from the line perpendicular to the plane, or 90 degrees to the plane. So this is our normal, right? So that would mean the angle of incidence is between here. So the angle between here. And based on the law of reflection, the law of reflection has 2 conditions. The incident ray is equal, or the angle of incidence rather, is equal to the angle of reflection. So that means that this angle A is equal, or let's say I. The incident angle is equal to the reflected angle R. So I is equal to R. Now, this here would be the refracted ray. And remember, refraction occurs whenever a light ray is passing, or not only a light ray, but a ray is in this case, a light ray is passing into different materials. So in this case, it is going from air, the boundary here, into ice or water, right? And here, that would be our boundary. So of course, because the speed of light will change, the angle will be refracted, because basically the light ray, the speed of light is going to slow down in different materials, or change its speed in different materials, hence why the ray is refracted. Now on NO, the refracted ray is now our line of incidence or ray of incidence. So this here is showing total internal reflection because it's within the material itself. And I'm seeing another ray here. But let's look at the questions. Most likely, that would mean that this here, this angle is equal to the critical angle, because now this here is 90 degrees. And if the incident angle is greater than the critical angle, then you'll have total internal reflection. So let's look at the questions. So I want you to determine the angle of incidence on the face MN. So basically here. Now, as I said, if we look here, this is 90 degrees. So far, this has covered 31 degrees. So we need to find out the rest here, which we could use 90, or let's say angle of incidence I is equal to 90 degrees minus that 31 degrees that we already know. Therefore, the angle of incidence is equal to 30 minus 90, 60 minus 1, which is 59 degrees. So our angle of incidence is 59 degrees. And the angle of reflection on the face MN is the same. And remember, I is equal to R based on the law of reflection. So if we found this to be 59 degrees, that means this is 59 degrees as well, right? So that would mean I is equal to R, therefore R is equal to 59 degrees. They want you to find the angle of refraction at the face MN, given that the refractive index of ice is 1.31. Now, based on Snell's law, the sine of the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to the refractive index n, right? So basically sine I over sine r is equal to n. Can also represent this by the speed. So basically the speed of the first material over the speed of the second material, or the speed of light in the first material divided by the speed of light in the second material will give you the same constant, which is the refractive index n. But seeing that we don't have the speeds, we'll definitely be using sine I over sine r, because we do have the angle of incidence. So basically what we'll have now, sine 59 degrees or just sine 59 for now, divided by sine r, which we don't know the value of r, is equal to 1.31. If we do a bit of transposition, what we want to do is get r by itself. So sine 59 over sine r multiplied by sine r will allow sine r to be cancelled out, is equal to 1.31 multiplied by sine r, because what we do on one side we have to do on the other side, and see that we multiplied by sine r, we have to multiply by sine r on the other side. Now we have sine 59 is equal to 1.31 multiplied by sine r. Now we need to get rid of this 1.31 because again we're trying to get sine r by itself for now. So divide this by 1.31, and whatever you do on one side you have to do on the other side, so 1.31, and again 1.31 cancels 1.31. So now our equation will read sine r is equal to sine 59 divided by 1.31. Seeing that r is an angle, to find the angle, r will be equal to the inverse sine of sine 59 over 1.31. So if you put that in your calculators by holding, first what you want to do is hold the shift and sine, then you want to put in, if your calculator doesn't give you the brackets, put it in brackets, sine 59 divided by 1.31, and your answer should be sine inverse sine 59. Is it 59? Yes. 1.31. So I got 40.9 degrees, which is approximately 41 degrees. So that would be a refracted angle, right? Then said on the diagram in figure 3 on page 11, label the critical angle for ice. So give me a sec, let's move this back up. Let me clean this up. Alright, so now that I have this cleaned, hey, I had to trim that because I made a mess of this last question, and when I realized that I made a mess of it, it was like too far gone for me to like say, hey, I made a mistake, so I'm just going to show you how it's done. No, I could have done that. Because then it wouldn't make any sense. So we worked out, after cleaning the screen, so we worked out this to be approximately 41 degrees from the normal. So incident here, this would be 41 degrees as well. And now given the relationships where the angle of incidence is less than the critical angle, then you would have a refracted ray. If the I is equal to the critical angle, then you'll have 90 degrees. If it is larger, if the angle of incidence is larger than the critical angle, then you'll have total internal reflection. So basically, as the angle of incidence gets larger, you will find out that as it gets larger, it gets closer and closer to internal reflection. Or you can think about the refracted ray would be about like here, and as you increase the angle of incidence, it will move closer to this point. Now, seeing that you've gotten 41, right? 41 degrees. 41 degrees is 41 degrees provides you with a total internal reflection as shown by this ray here. So that would mean that this angle here is greater than the critical angle. So to get it back to equal to the critical angle, we'll have to decrease it. So the critical angle would be somewhere between this point. So I guess you can label it like that. Also, as I said, I'm going through content. How much smaller though? I don't know. Let's make it that small. So you'll relabel that theta C. So also, you'll find that sine C, where C is the critical angle, is equal to 1 over the refractive index. Alright, so I guess that should be good. Yeah, I think that was the last question. And you'd get your 15 marks. Alright, so if you have any questions, don't be afraid to leave them in the comments. Also connect with me on social media. My socials will be linked in the description down below. If you don't want to go look down there, you can go follow me at _CAM_EO. My name is Camulipado. Yes, or you can go follow my business. I shouldn't even say or. And please go follow me on my business page at young_genius.official. So I hope this was helpful, and until next time, bye guys.